So for the Bayesian inference, we apply this Bayes theorem, which we discussed in the previous topic. And you can see that actually this theorem is simple explanation of the definitions of conditional probability and their relationships. Uh, so we have already defined the joint probability of, say, two events, A and B, and that can be expressed in the form of the conditional probabilities with respect to the other event that you can see in the very first expression, that it could be equivalently expressed as either probability of A multiplied by probability of B given A, or the other way, probability of B multiplied by probability of A given B. Now these equalities, actually the last equality, which means I'm just referring to this relationship, which is basically implied by from the joint probability distribution itself. This one is giving you the corresponding Bayes theorem, which can be written otherwise in this form. As you can see that here, instead of denoting it by A and B, we consider a hypothesis and data in the context of our classification problem. And hypothesis is a classification that hypothesis for classification. It is basically trying to model a target function. And data is your observation set. That is the training examples, or yeah, that's the training examples with this. So given the data, which hypothesis you are considering, that what is the probability that hypothesis is in fact is true, which means this hypothesis is applicable. So so that is the kind of conditional probability, and that should be equal to, as you can see in the numerator, it is probability of the hypothesis multiplied by probability of data given hypothesis and divided by probability of data. So it is simply this relationship is coming from this particular expressions, this particular equivalence relationship. So if we if you consider these components of this particular relationship, as you can see that the probability of hypothesis, this is considered as the prior probability. That is the probability of the hypothesis on previous knowledge. So there is a probability. This is some kind of prior knowledge that what is the what I mean, some preferences over certain hypothesis. So if I say that there are two kinds of bias we have told. One is restriction bias, and another was is preferential bias. Now that preferential bias of hypothesis, that is nicely modeled by this prior probability in the probabilistic framework. And then you have the other term in the numerator, which is the probability of data given that hypothesis. So if I consider the hypothesis is true, then what is the probability of observation of that data set? Now, what is the, we also say in a term, maybe a bit common term, like what is the likelihood of observation? Now that has become technical. So we call it as a likelihood function, which has this probabilistic definition, that what is the probability of that observation given the hypothesis. That is, it's the same as if I ask what is the likelihood of that data. If I ask this question to you, you should understand that what is the probabilistic implications behind this particular question, which means we have to describe this probability. So this is what? So this is the likelihood function. You should note all these technical terms, because all our subsequent discussions will be using simply these technical terms, and you have to understand their definitions, probabilistic definitions from those terms. Then you see that in the numerator, in the denominator, you have the probability of data, and that is called here unconditional probability. But there is another term which is called marginal probability. That is also sometimes used. And in fact, no, this is coming from this particular relationships of conditional probabilities from the joint probability expression. But in the Bayesian theorem, you see that this particular denominator term is normalizing the probabilities of the hypothesis given data, which is called actually posterior. So this is called posterior probability, and since this is a probability, it should have a value between 0 to 1, and unless you give this denominator, you are not going to get the probability value in absolute sense. So we will come to that part later on also in our subsequent discussion, that what is the implications, what is the importance of this marginal probability, and sometimes you may ignore it in your classification task, but no, it has a lot of importance while you are doing some inference. And finally, the left-hand side expression, left-hand side term, which is also very much relevant, and whose technical term you should understand. We call it posterior probability. Sorry. So you see that this term, why it is very interesting, because this is what you would like to know, that what is the probability of that hypothesis. So hypothesis means, if I say we have a hypothesis, one hypothesis for assignment of a class and decision. So basically it is what is the probability of a class. We can say that what is the probability of a class itself as a hypothesis. So to a particular class given the data. So this is what you would like to know, and then you should take a decision accordingly. So there are two learning scenarios. If I consider this Bayesian theorem, it gives us two options of taking decisions about a class for an instance. One scenario is that maximum a posteriori hypothesis. From the term, you understand that we have told what is posterior. So you see that I just mentioned, say this is the posterior probability. So when we say maximum a posteriori hypothesis, which means we'd like to maximize that posterior probability of the hypothesis. So given a set of hypotheses whose posterior probability is the highest, we would choose that hypothesis. That is the scenario for maximum a posteriori hypothesis. And of course, the second scenario of maximum likelihood hypothesis, we will come to that. So let us first consider this expression. As you can see that, as I mentioned, that we are trying to maximize the posterior probability of a hypothesis. So if I have if I have to choose from a set of hypotheses, so I will choose the hypothesis which will have this maximum probability. Now, if I consider that my observation is fixed, that means with respect to a given set of observations, I would like to maximize it, then naturally the denominator term, that is probability of the data or marginal probability of data for that given set of observations, that remains the same for all a posterior probability of the posterior probabilities of all these hypotheses. So that's why we can ignore the denominator term while computing this particular, while taking this decision. We can just simply find out the hypothesis which maximizes the product of the likelihood and prior. So you can see that this is what I am mentioning. So this is the this is a term that is, if it is sufficient, if I compute the probability product of these two, that is, if this part is called likelihood part, that is likelihood of data given the hypothesis, and this is the prior part, that is the probability of that hypothesis. So if I consider all possible hypotheses, and for each we compute this product, and then find out the hypothesis which give me the maximum, that hypothesis should be chosen. I hope you understand this particular meaning of this particular function, argmax is the point where the maximum occurs, or the value or the instance in that particular set where this maximum occurs. So it generates a hypothesis. Its output is an hypothesis. Its output is an element of this set H, capital H, which means the set of hypothesis or hypothesis space, and an element of that hypothesis space. That is the output, and that hypothesis which maximizes this probability. Now, this is about this maximum a posteriori hypothesis. That is the scenario. And that's I mentioned that because probability of data is same, you can consider this. Now let us consider the maximum likelihood hypothesis scenario. So it is very simple. As we have seen from the case of a posteriori hypothesis scenario, we are anyway computing this likelihood of the data given hypothesis. So in the maximum likelihood hypothesis, which we have less computation, we can simply compute this likelihood for every hypothesis, likelihood of the data for every hypothesis, and choose that hypothesis which maximizes this likelihood, which means I can write in an equivalent way that what is the hypothesis where this maximization occurs. Any question till now? Okay, so let me proceed. So let us consider an example. Here, we would like to find out, say, whether a patient is suspected having a particular form of cancer, and for whom a diagnostic test has been reported as positive. So, we would like to compute. Of course, we need some probabilistic model, some knowledge about these particular domain and related events. So, what are the information we have? So we have that the probability of cancer is 0.008. Naturally, the probability of not having cancer is 0.992. So this is one kind of piece of information. So any one of them can be given. You can always derive the other one, as you can see. And then there are, suppose, two now classes. One is the cancer class, another is the non-cancer class. That means you consider the subject suffering from cancer, that is, and then you consider if you carry out the diagnostic test, what is the probability that diagnostic test will report positive? Now here you see that it's very high, it is 0.98, and then what is the probability that given that cancer it is negative, it is 0.02. Okay, so these are the two things. I understand that if you are going more on machine learning things, you can consider given a particular diagnostic test, what is the specificity and what is the sensitivity that you can compute from this particular information that is specified here. So here, of course, you have this, that you have this positive given cancer and negative given cancer, those informations are given. Similarly, if you have if you consider the other cases, that means the population who do not suffer from cancer, and if you carry out this diagnostic test, still it can be a false positive, and so the probability of that positive, given that the person is not suffering as a cancer, is 0.03, and probability of negative, that the person is not suffering from cancer, given that it is 0.97. So these are the information. As you can see that some of the information is redundant and some of them are essential. So can you tell me which are the what is the minimum set of information that I should have in this context? How many pieces of information?
Sir, 3.
Yeah, that's right. So you see that though I have given you all the informations in a very explicit form, actually if I specify only 3 of them, and of course they have to be appropriate. They should not be again redundant. So then you can derive the other pieces of information from there. Now the question is that here you have to solve this problem. That what if we consider these two scenarios? That means one is the scenario of, say, maximum a posteriori probability. Suppose you have two hypotheses. One is, say, H1, which is that the patient is suffering from cancer, and H2 is patient is not suffering from cancer. And then you would like to compute when it is maximum a posteriori scenario, what you are going to compute there? You are going to compute, can you tell me what you are going to compute given the observation that the reported test is positive? Then for the maximum a posteriori scenario, what you are going to compute? Any idea?
Probability that he has cancer.
Probability of cancer given test.
Can you be very precise? Probability that he has a cancer means
H1. This is H1. Means in this
probability
case.
of H1 only.
Means in first case for cancer we will see for probability
So how
of
the data plays a role there. So if I say probability of H1, you see that we know probability of cancer is 0.008.
So positive cancer and positive given not cancer. So from that.
So probability of cancer given positive. So you have to be very precise. You be mathematical now when you are describing it. So probability of H1 given the patient, the diagnostic test is positive. And the other one, probability of H2 given that the diagnostic test is, tell me, what should be the other one?
Given negative?
No.
The test.
What is the observation? That's what I was thinking that you will be confused.
Positive.
Yeah. So observation is positive. So you are considering that only. So what is the probability of H1 given the report positive? What is the probability of H2 given report positive? Both the cases. The observation is same. Then what you are trying to do? You are trying to find out which one is the greater, isn't it? And then you choose that particular hypothesis. Now that is the scenario of maximum a posteriori. What should be the maximum likelihood scenario? What is the maximum likelihood scenario?
Positive given cancer and
Probability of observation. What is the observation? Observation
Positive.
is positive. So probability of observation positive given cancer class. Given the hypothesis, right? Given H1. And probability of observation, once again, tell me, what should be the other one you should compute?
Positive given not cancer.
Exactly. And actually that is already given, so you need not compute. So maximum likelihood thing you can immediately decide, na? Given the maximum likelihood scenario, so what should be your decision? Which one you should consider? H1 or H2?
H1.
Pardon?
H1.
H1. So what are the probabilities in that scenario?
0.9.
0.9. See, somehow now your voice is missing. So please tell me full, because there are so many 0.9s are here.
So for maximum likelihood it is 0.98. For
0.98. So what is the other probabilities? Can you tell me?
0.98 and 0.03. H1 and H2.
Exactly. That is what, right? I hope it is clear to all of you. Is there anyone who has a problem to understand that this maximum likelihood based decision making process given this particular information?
Sir, can you come again once?
Okay. I will basically go forward and you will find it once again. Okay. So let me see. So so the map approach and ML approach. I will come to the ML approach once again later on, because I think map approach. So why don't you compute both of all of you compute. In map approach, what you are going to compute? You are going to compute the, if I consider map approach, simply it is a product of prior and likelihood. Because no, your data, you can consider that given the data is same, remains same for all hypotheses. So for every hypothesis, you can simply compute the product of prior and likelihood, and then choose that hypothesis, which one gives you the maximum value. Any confusion? So please do it and let me know. Anyone? What about Ayush Prasad? Are you present, Ayush?
Yes, sir. Sir, I
So-
have got for cancer 0.00784 and for
Okay.
not cancer 0.02976.
So which one you should take?
The
Not
greater
cancer.
one, that is not cancer.
Okay, very good. I hope this is fine. Okay, you might be a little bit in a computer. You got 9.6, maybe no. I got yeah. There is error. It should be 6. I think it. And anyway, you have to check it. Huh? Why
No,
it is
sir,
point?
it's correct.
It is correct, no? Okay, fine. So you are taking, selecting this. The patient does not have cancer in the MAP approach. What about ML approach? What was your verdict?
H1,
Direct.
H1.
Direct.
Yeah. So the person who has asked to repeat, I hope now he should understand that these are the two things already given, and we are choosing them only from the data set in the maximum likelihood approach, where your maximum likelihood is computing the probability of the data given the hypothesis. That is what is likelihood. So what is the data? Data is that positive. Diagnostic test is positive. What is the hypothesis? Hypothesis that patient is having cancer. So probability of positive given cancer is 0.98, which is already there in your data set. It has been given. Similarly, probability of positive given not cancer is 0.03. That is also there. So now what should be your verdict? Your verdict is H1, right? So you see that no, given two scenarios, just you have opposite decisions. So that is the importance of Bayesian inference. And we always say Bayesian inference is most sound because you are using using also the prior information that is trying to making the domain more consistent to your particular, I should say model is more consistent to our domain knowledge. So prior has a very important role in making this decision, though computing prior is not trivial, right? That's it. That or getting prior information is not trivial. So definitely, I mean, if there is any error in modeling prior, your decision making will be also erroneous. But it has a very important role. And this inference is known as Bayesian inference. So when we say Bayesian inference, then you should always consider this map approach. Bayesian inference is not ML approach. Okay, any Bayesian decision making, it is guided by map approach. And when we say specifically maximum likelihood based approach, we'll say it is a maximum likelihood based approach. I hope these technical terms should be clear, because these are mostly used, the people will not explain you that Bayesian inference means you are going to map up. Actually, you are doing it. They may not explain you, but you have to now understand and you have to apply it accordingly. So let me proceed further. Now, there are something more also we can compute from these data sets. And they, as I mentioned, that actually in the map approach, did you compute the probability of posterior? Did you compute the posterior probability there? If I go back, say, is the posterior computed here? Abhishek Srivastav, can you tell me, is the posterior computed? So Abhishek, are you here? Maybe Ayon, are you here? Ayon Chakraborty? Say, I will go randomly and I will ask. Kuheli, I think
Yes.
Kuheli is here.
Am I audible?
Yeah. Who is speaking, please?
Oyon, sir.
Ayon. So yeah, Ayon, tell me that which one do you compute? Are you computing posterior here in the map approach? What we have computed here?
Yeah, but we're not considering the denominator part.
All right, that's right. Which means that no, you are not computing posterior, right? So what is the importance of computation of posterior in that case? Let us see. You have taken a decision, but still no. If you compute posterior, you will have a better understanding of your decision. So let us proceed further. Thank you, Ian. Okay. So let me then compute that. So for that we need to compute probability of data. That means what is the probability of a patient of the diagnostic test is positive over the whole population, right? That is what is probability of data. Okay. So please compute and let me know what is the probability that the diagnostic test will report positive. I will go back because now I can give you all the information what is being given to you. Use that information and you compute what is the probability of a diagnostic test will report positive. So I will ask Kuheli, because Kuheli, you try and tell us. How do you proceed, Kuheli? Can you tell us? Kuheli, any idea? How do you proceed? How do you proceed to compute this probability whether the test is positive or not?
Sir, given that, okay.
See, there are two scenarios, no?
Yeah.
There are two scenarios. One is having cancer and not having cancer. So you are trying to consider these two scenarios. Under these two scenarios, what is the probability that diagnostic test will report positive? So that you need to compute. So you should divide it into two scenarios. Say a person is having cancer, and what is the probability that the diagnostic test will be positive? In the other scenario, the person is not having cancer, and what is the probability that diagnostic test will be positive? So if you add them, you will find what is the probability that the test will report. If is anyone, so Kuheli, you can mute your microphone. Is anyone got the answer?
Yes,
Yeah.
sir.
The
For
positive
positive
is
is 0.0376 and for negative is 0.96.
Okay. Is it okay?
Yes, sir. Yes, sir. It's correct.
Okay. You see that again, if you compute what is the probability of positive, then naturally the negative will be computed like this. Huh? So this is how you can compute the probability of data. So once you have probability of data, now you compute the probability of posterior probability of this hypothesis. What was the decision? Posterior probability for a hypothesis that the patient is not suffering from cancer, isn't it? That was the decision, no? That posterior probability. What was the decision? Which was the maximum? Anyway, you can compute the posterior probability. Yeah. So find out what is the probability that posterior probability that the patient is not having cancer. So Mohammad Ladla, are you okay now? I could see your presence, but no, you had.
Yes, sir, yes, sir. I'm trying to attend classes
But
anyhow.
no, you should not exert yourselves. You should take rest.
Yeah, yes.
And you can watch also video later on. Anyway, I mean, you be there in the class if you can. Fine. I hope you will recover.
Yes,
Okay.
thank you.
Okay. So please tell me then what is the posterior probability? Who can tell me? Meher Changiani, can you tell me?
Yes, I'm calculating it.
Pardon? Meher? I could not get you.
I'm calculating it.
Oh, you are calculating. Okay, fine, good. Just if you see that you had for this case 0.0298, that was the product, right? So what you should do now? That product should be divided by the data, probability of data. What is the data here? What is the probability of data here? What you have computed?
0.0337.
That's right. That is the data, that is the observation. So you have these two things. So that probability was 0.79. So now in absolute sense, you are getting this probability, posterior probability. So you can see that what is the degree, some kind of confidence it is giving. You know that no, in lieu of that, what is that the patient could have been also this declared as a cancer. So there is a 0.79 probability on which you are taking this decision. So that gives you some kind of degree of your confidence in your decision. In fact, if I consider that's a Bernoulli distribution, then you can consider what is the variability of your decision. This is the range over which this posterior will lie, and it's quite a bit of variability, as you can see. So SD, standard deviation, is this. Do you agree with me, this standard deviation computation? If you consider it's a Bernoulli decision, Bernoulli process.
Yes, sir.
Yeah, so root over P into 1 minus P, right? And it is the same. If you take the other one also, it is there. So it depends on, very nicely consistent with your decision making process. So you see that it gives a different, different information. It gives more information. So that's why computation of posterior is also important in many cases. Okay, though it is non-trivial and sometimes it is very complex, and you can avoid it just if you want classification.